induced EMF and induced current in the rectangular loop moving in non-uniform magnetic field. So ABCD is a rectangular frame or rectangular coil. Here is a magnetic field. Magnetic field is perpendicular to the plane of the coil ABCD. Here up to this there is a B1 magnetic field. Afterward there is a B2 magnetic field. So the magnetic field is not uniform. Here up to here B1 and after this B2. B1 magnetic field is higher or more than B2 magnetic field. So this is the direction of magnetic field. B1 and here B2. So if the frame is moving with the velocity v in the right side direction, then in delta t time it will cover a distance v into delta t. So what will be the change? So this distance will be equal to v into delta t. Now this will be the position of a dash, new position after t, a dash, b dash, c dash, d dash. This is v into delta t. Here also a dash is equal to b dash is equal to v into delta t. So what will be the area? Area will be equal to a dash d dash t. This will be equal to length. This length is L. This is there. So area will be equal to dA. The change in area will be equal to length divided by the breadth. Length is L, breadth is v dt delta t. So the area will be equal to v into L into delta t. Now since magnetic field is perpendicular to the coil, so the magnetic field is parallel to the area vector, because the area vector, direction of area vector is perpendicular to the plane of the coil, that is ABCD. So delta A and B are parallel to each another. So what will be the decrease in area? Here area will be decreased, so flux will be decreased. So decrease in the magnetic flux will be the magnetic field multiplied by the area. So the decrease in the magnetic field of B1 will be equal to phi 1 is equal to B1 into delta A into cos theta. Now theta is equal to 0 because B and dA are parallel. So it will be equal to B1 into delta A, and we substitute the value of delta A, then it will equal to B1 into V into L into delta T. So this will be the decrease in flux of magnetic field B1. Similarly, for the second part, if we take for the B2 magnetic field, then here the magnetic area is increasing. So the magnetic flux will be increasing when it is moving with the velocity v. So increase in the magnetic field of increase the magnetic flux of the magnetic field B2 will be equal to phi 2 will be equal to magnetic field B2 multiplied by dA. Here also theta is equal to 0. So B dot dA is equal to 0. Cos 0 is equal to 1. So phi 2 will be equal to B2 into delta N. This is equal to B2 and the value of delta is VL delta 3. So this is the increase in the magnetic flux. This is decrease in the magnetic field. So net increase in the magnetic field will be difference of these two. So the net increase in the magnetic field will be delta phi, which is equal to phi 2 minus phi 1. So delta phi will be equal to, we subtract it, VL delta T is common. So it will be equal to B2 minus B1 into VL delta T. So what will be the delta phi bata delta T substitute. So delta phi bata delta T will be equal to B2 minus B1 into V into L. So now we know that from the Faraday's law, if there is a change in flux, then induced EMF is produced, and rate of change of magnetic flux is proportional to the EMF produced, and the EMF will, the direction of EMF is given by the Lenz's law. So using the Faraday's law and Lenz's law, Faraday's law and Lenz's law, we write EMF will be equal to minus delta phi bata delta T. So it will be equal to minus B2 minus B1 into V. So it will be equal to B1 minus B2 into L into V. So this will be the EMF produced will be equal to this. So here what will be there? This will be the B1 is positive. B1 is more than B2. So this end will be positive. More positive than this end. So current will flow in this direction. So current will flow in anti-clockwise direction. So what will be the current? Current will depend upon the resistance. If the resistance of this ABCD coil is R, then the induced current, this is the induced EMF, this is the induced current, will be equal to EMF divided by R, that is equal to B1 minus B2 into L into V divided by. So this will be the value of induced current which will flow in the coil due to the motion of the coil in the non-uniform magnetic field. And suppose if the magnetic field is uniform, means B1 is equal to B2, then this current will be equal to 0, EMF will be equal to 0. So there will be no induced EMF or induced current if this coil, rectangular coil, move in the uniform magnetic field with constant velocity. It makes no difference. So the induced EMF and induced current will be 0 when V1 is equal to Vt, or we can say if the rectangular coil move in the uniform magnetic field, then no induced current and no induced EMF is produced. Conservation of energy. When a rectangular frame is moving with constant velocity in non-uniform magnetic field. So this is the rectangular frame PQRS. The magnetic field is perpendicular to its plane. Here up to this point is the magnetic field B1. Here it is B2. B1 is greater than B2. Now, as we have learned in the previous lecture, that when the rectangular frame moves perpendicular to the magnetic field, which is non-uniform, then induced current is produced, and the direction of induced current will be PQRS, means it is in the anti-clockwise. This will be anti-clockwise. Now this arm is PQ, this is RS, and this is SP. Now when the current is flowing, magnetic field is there, then there will be a force on the sides PQ, RS and PS. All the sides there will be force. The direction of force will be given by the Fleming left hand rule. So the force will be equal to I L cross B. I is the current flowing, L is the length, B is the magnetic field. Since they are perpendicular, so the force by the Fleming left hand rule will be equal to I multiplied by the cross product of length and magnetic field will be equal to I L B sine, and the angle between current and B is 90, so sine 90 is equal to 1. So this force will be equal to I L into B. So if the current is flowing I, B is the magnetic field which is perpendicular to the length L, then the force will be equal to I into L into P. Now we consider the different parts. Suppose we consider the part PS, this part PS. Now current is flowing in this direction. So from the Fleming left hand root, the force will be in this direction. This will be in this direction, will be towards the left. And this force will be equal to F1 will be equal to current I will be same for PQ, RS and SP and QR. All the current will be same in all the sides of the rectangular frame. So F1, this force will be equal to I into L into B1, because magnetic field is B1 here and its direction will be left. Now if we consider the RS branch, then PQR branch, which is opposite to PS branch. Here the direction of current will be opposite. Here the direction is this side. Here current is opposite side. So the direction of force will be also opposite. Then by using the Fleming left hand rule, the force on QR branch will be equal to F. We consider suppose it F4 is equal to I into L into B2, because here magnetic field is B2, here magnetic field is B1. So it will be F4 will be to I L B2 and it will be towards the right. Now we will consider for the branch PQ and RS. For PQ branch, half the portion the magnetic field is B1 and half the portion magnetic field is B2. Direction from P to Q, direction of current from P to Q and R to S are in opposite direction. So the force of this half portion will be, suppose we consider the F1, F2, and here we consider the F6. Then F2 and F, since the direction is opposite, so and magnetic field is same, so F2 will be equal to F6 will be equal to I into L dash, suppose this length is L dash into B1. Similarly, for the second part, that is for half part of PQ, that will be equal to F3 force and F5 force. They are in opposite direction, current is opposite direction, so the forces will be opposite direction, and the magnitude of this force will be equal to I into L into B2. This will be the magnitude of this force. but these forces are in opposite direction. So net force will be equal to, this force will be cancelled by this force will be cancelled by 2. But this force will not be cancelled by this because they are of unequal magnitude. Although the direction is opposite, but the magnitude is not same. So total force on this frame will be equal to F1 plus F2 plus F3 plus F4 plus F5 plus F6 plus F6. So F2 is equal to F3. F2 is equal to minus F6. This is minus F6. F3 is equal to minus F5. So these cancel. And F4 is, so net F4 is in opposite direction. So it will be F1 minus F4 because F4 is towards the right, F1 is towards the left, F1 is greater than F4, so the net force will be towards left and net force will be equal to F1 minus F4, so which will be equal to, we subtract F1 minus F4, so it will equal to B2 minus B1 into I into L. So this will be the net force and it is towards left. This force will be towards left. Now what will be the work done? The work done will be equal to force multiplied by the displacement. Now force is in this direction. Displacement is, it is moving the velocity v and delta t is the time. So displacement will be equal to v into delta t. Force and displacement are in the same direction. So that will be equal to cos theta and theta is equal to cos 0 and that will be equal to f into v into delta t. So this will be the work done. So work done will be equal to, we substitute the value of force, that is equal to B1 minus B2 into I into L multiplied by V into delta t. So this will be the work done in delta t time for the rectangular coil to move with the constant velocity v. Now what will be the induced current? We have earlier lecture we have find the induced current. Induced current is equal to B1 minus B2 into V into L bata R. We substitute the value of current here in this expression. Suppose this is the equation number 1, this is the equation number 2, then substitute the value of current from 2 to 1, then this will be equal to B1 minus B2 into V, that is equal to B1 minus B2 bata R into V into L into V into L into delta T. So this will be equal to B1 minus B2 ka square divided by R into L square V square delta T. So this will be the work done when this frame is moving with constant velocity for the delta T time. The total work done will be equal to B1 minus B2 square into L square V square delta T bata R. Now where this work will go? Now we can find that this work done will be converted into heat. Then what will be the amount of heat it will produce? Now by Joule's law, the heat produced will be equal to I square into R into delta T. So heat by Joule's law, heat produced will be equal to I square R into delta T. We substitute the value of I from here. Then H will be equal to B1 minus B2 chi square, V square, L square, R square into R into this. One R will cancel here. So it will be equal to B1 minus B2 L square V square delta T bata R, and this heat produced is equal to work done. So we can say that here the work done is converted to heat. So there is a conservation of energy. We can also have in the table the power also. Power, what will be the power? Power is equal to work divided by time. So power will be equal to same I square R, or here R will be cancelled. So dt will be not there. So again the power, which is the mechanical power, will be equal to electrical power. This is electric power. Mechanical power will be equal to delta W divided by delta T. So both will be equal. So either we can say by the conservation the work done is converted to heat energy, or the power in the mechanical power will be equal to electrical power. So in this way we can say when we move a rectangular frame perpendicular to the non-uniform magnetic field, then the energy is conserved, the mechanical energy or work done is converted into heat. So we can say there is a conservation of energy in the case when the rectangular frame is moving with constant velocity perpendicular to the non-uniform magnetic field. Currents. So first I explained you eddy current in terms of the experiment. Suppose we are having a metal plate and it is suspended by a thread and we oscillate it. It will oscillate to and fro, and due to air resistance it will stop by after certain oscillations, and suppose it is stopped after 20 oscillations. After 20 oscillations, the oscillations of the pendulum is vanished or stopped. Now, if we put this pendulum here in between the magnet, here the N and the magnetic field is P, and now it swings in between the magnetic field, then it is observed that after 5 or 6 oscillations, the pendulum stops, means the oscillations are vanished. Now, how to explain it? Now, when the magnetic field is there and we oscillate it, then the oscillations stops after suppose 10 or 6 oscillations. Why it happens? Now we can explain it with the help of eddy currents. Now what is eddy current and how eddy currents are produced, we can explain it. Suppose we are having a metal plate. This is the metal plate. In metal plate there are many free electrons. Free electrons are there. Now when this metal plate enters in the magnetic field, now it goes from 0 magnetic field, 0B to 0B, or B is equal to 0 to increasing B. B is increasing as it go inside. So what will happen? The electrons will experience a force. Now why it will be experienced? Now when there is a change in, when it will enter, its area is fixed, magnetic field is increasing, so magnetic flux is increasing. So when the magnetic flux is increasing, then induced EMF is produced and induced current will be flow. So the induced current will be due to the free electrons, and free electrons will move. It is not necessary that they move in the circle. There can be any closed path. It can be this closed path. It can be any closed path. So the induced current is produced in the plate. Now this induced current from the Lenz's law, it will oppose the motion. So now when it enters, if the induced current is in the clockwise direction and when it is going outside, then what will happen? Now the magnetic field will be decreasing from V to 0. So now magnetic field is decreasing. So the induced current will be in the opposite direction. So here current was in the clockwise direction. Here the current will be in the anti-clockwise direction. And this induced current will always oppose the motion. So there will be a damping, means the oscillations are damped, means the oscillations, the amplitude of oscillations will be continuously decreasing and ultimately it will be stopped. So we can say when the metal plate which is oscillating between the magnet experience a damping force, and that damping force is electromagnetic damping, and this is due to the induced current which is produced due to the change in the magnetic flux. From the Faraday's law and Lenz's law, according to Lenz's law, it will oppose it. Now, when it is returning in the back direction, then it is going from 0 to maximum. Now here, in this case, the direction of induced current will be in opposite direction from this to this. And here when it is going out, it will be. So, in both the cases, when the pendulum is entering and pendulum is going out from the field, the direction of induced EMF and induced current are in opposite direction, and this induced current will damp the oscillations, means the oscillations will be decreasing and after few oscillations it will stop. So such type of current is known as eddy currents. This term is similar to the eddy currents in the sea. In the sea, or if you have a water in a bucket and you rotate it, then the eddy currents are produced. Suppose this is the bucket and you rotate it, then you will see that there is a eddy currents are there. There will be eddy currents are there. And here there will be no water. So similarly here, the eddy currents are there. So eddy currents are produced. When eddy currents are produced, eddy currents are produced when there is a change in the magnetic flux. When there is change in the magnetic flux, then the free electrons in the metal plates are produced. The concentric or the closed path of the induced current, and this induced current will always oppose the motion by the Lenz's law. So this such type of current is known as the eddy current. So we can say eddy current is a phenomena which is produced in the metals when the magnetic flux is changing. The eddy currents are produced. So this is about the, now what are the use and how the eddy current is used in the different circuit. Suppose we take the core of transformer. Now in transformer we use the AC current, and in AC current the current changes, the current is AC. So the magnitude of current changes. So magnetic flux is changing. So when magnetic flux is changing, then the magnetic field will be changing. So there will be ED current in the core of the transformer, or we can say the core of the electrical motor. One and the same thing for the electric motors and for the core of the transformer. They are made up of iron. So induced current is produced, and so ED currents are produced, and due to ED current there is a loss, and the loss will be in terms of the energy. So how to reduce this ED current? So what we do? We take several plates. This is the one plate, second plate, third plate, fourth plate, and this all the plates make a core. Then we put here insulation varnish. So for the insulation varnish, the resistance is infinity. So the current will not be passing. So we can reduce the ED currents by laminating. We can also call it lamination of the plates, or insulation varnish is placed or painted on the plate so that the resistance between the two plates is infinite. So the resistance increases, so the ED current is decreasing. Now we can also show that here in metal plate, if we have a metal plate and we have a slot in the metal plate, same we have a pendulum and metal plate, and if we oscillate it, then it will do 15 oscillation. It will make more oscillation than it is a complete plate. Why? Because here the ED currents will be produced in this small area, and here resistance is infinite. In the gap there is air, and resistance of the air is infinite. So the ED currents are reduced. So since ED currents are reduced, therefore it will oscillate more than when it's a complete plate or it is not, slots are there. So in this way we can explain this. Now second, we can take the example of magnetic brakes. Now in electrical train, magnetic brakes are used. So this is the wheel. Suppose this is the wheel. Here there is a magnetic field are there. Now when we want to stop the train, then we pass a very heavy current in this brake. Now due to this heavy current, the wheel is rotating. So induced EMF is produced and ED currents are produced, and due to this ED currents, this will be in the opposite direction, so the train will be stopped. So ED currents are used for the electrical brakes in electrical train. Now deadbeat galvanometer. So we use galvanometer in the laboratory, and that galvanometers are deadbeat results. Now what do you mean by deadbeat result? Now in the galvanometer, this is the coil, and coil is framed in the metal, and metal generally it take a, suppose aluminum metal, it is non-magnetic metal, aluminum metal. So when it rotates, if this frame is, suppose paper frame, this frame is paper, then the needle will oscillate. It will oscillate, and after some time it will stop. But if we take a metallic frame here, then when it moves, then the magnetic flux change and induced current is produced, ED current is produced, and it will oppose the motion. So it will stop just as, and we will get the constant deflection. So the deadbeat galvanometer, the frame of the coil is made up of light material, and that is the aluminum. If it is not aluminum, if it is the air, if it is a non-conducting, suppose it is a paper or cardboard, then it will oscillate many times, and after many oscillations it will give the deflection. But for the instant deflection, what we do? We will have a metallic frame. In the metallic frame, when the current is passed through it, then it will rotate, then magnetic flux will change, induced currents or ED currents are produced, and ED currents will oppose the motion, and it will stop, and we will get the constant deflection within the microsecond time. Now, next is an induction furnace. Nowadays, we are also having induction cooker in our house. Now, one induction furnace is there. In induction furnace, suppose this is the induction furnace, and here there are coils surrounded. And in this coil, we will pass heavy current with high frequency. Then what will happen? Then this ED current will produce the heat, and suppose we are having metal here, then the temperature is increased to high, so this metal will be bent. So alloys are produced using, we have the different metals, and we put them and then the induction furnace, and we pass heavy current with the high frequency. Then large ED currents are produced, and large ED currents will melt both the metals, and the metals will be formed an alloy. Now, next use is aluminum disc in the electrical meter. Now we are having the electronic meter, but earlier we were having a meter in which you will see that there is a aluminum disc, and aluminum disc is rotating. Now, why the atom is rotating? So here there is a coil, and in this coil the current passes, AC current passes, and which it will enter here and it will go to our home. So it is from the power supply or from the powerhouse, and this will go to. So the current will pass through it. Then when current will pass through, what will happen? Then due to the current is AC, so EMF will be changing. The magnetic flux will be changing. So magnetic flux will be changing, induced current will be produced, and this will rotate. If the more consumption of current is there, it will move fast. If the less current is consumption, it will move slow. And if no consumption of current is there, it will not move. So we can use the ED current for the measurement of the consumption of electricity in our home. So ED currents is useful for the core of the transformer or electrical motor, magnetic brakes. It is for the induction coil, for deadbeat galvanometer, and also for the measurement or the consumption of the electricity at our home.